Hi, today we're going to talk about how to see if a series converges using integral test. So an integral test is going to be based on the following. So if we have some kind of a continuous positive and decreasing function, these are the conditions. We can say that the function that we have is going to equal to the terms of the sequence. Then as long as the integral converges, then the series is going to converge. Okay, and if the integral diverges, then the series diverges. So here's our first example. We have a summation of 2n over n squared plus 3, going from 1 to infinity. There's one thing you have to keep in mind. Since this is going to go to infinity, you do need to make sure that you use improper integrals, because that's what's going to happen. So we are going to rewrite that. I can't put an equal sign here because these things are not going to equal to each other, but separately I'm going to write the integral from 1 to infinity of 2x over x squared plus 3. It's not really that critical to use x instead of n in this case, but it's typically how it's done, so I'm just going to do it. Okay, so this is our expression. We have, this is an improper integral, so we're going to have to use a limit as a approaches infinity. Integral from 1 to a, right, of 2x over x squared plus 3 dx. This is our situation when we use U substitution. So x squared plus 3 is u, and then 2x dx is du. And then we can replace all that. Do need to remember to recalculate the limits. So the limit as a approaches infinity of the integral. So the upper limit is still infinity, the lower limit will be 4. And that is going to be 1 over u du. And then that will be the limit as a approaches infinity of the natural log of the absolute value of u. You actually don't need the absolute value here because it is going to be positive all the time since you go from 4 to infinity, but it won't hurt. Okay, so we're going to get the limit as a approaches infinity of ln a minus ln 4, and we know a goes to infinity, so this whole thing goes to infinity, and this is going to diverge. So that means that our original series also diverges. Okay, that's as simple as this. Okay, next problem. We got this. So let's go ahead and set it up using integration. This is going to become the integral from 1 to infinity of 1 over x squared plus 1 dx. Okay, so again another improper integral, so we need to use the limit as a approaches infinity of the integral from 1 to a of 1 over x squared plus 1 dx. Okay, so what do we have here? This is going to give the limit. This is a very standard expression. This is arctangent of x going from 1 to a. It's going to be the limit as the approaches infinity of arctangent a minus arc tangent 1. Okay, so what do we know here? This is going to become the limit, well, when arctangent, there's no limit anymore. As a goes to infinity, arctangent of infinity is pi over 2. And arctangent of 1 is pi over 4. So it gives us a finite value of pi over 4, which means it converges. So we know that sigma from 1 to infinity of 1 over n squared plus 1 converges. Okay. Next problem. So we have this one. We do have to use, well, let me rewrite that using integration first. So what we have here is we're going to rewrite that as an integral from 2 to infinity. We can't start at 1, it doesn't really change anything. But if with 1 ln is going to equal 0, you're going to end up dividing by 0. We can't do it, so we started at 2. Okay, so it's going to be 2 over x times ln x squared dx. So right off the bat, we're going to need to start with U substitution. If you make ln x equal u, then 1 over x dx is du. So then this whole thing will become the integral from 2, no, hold on, it's not going to be from 2. When we use 2, it's going to become ln 2 on the bottom and still infinity on top of 2 over u squared du. We do need to use improper integration here, so we need the limit as a approaches infinity of the integral from ln 2 to a of 2 over u squared du. So that's going to give us a limit. A approaches infinity. So the integral here is, you're going to get negative 2 over u going from ln 2 to a. And what we're getting now is the limit as a approaches infinity of negative 2 over a plus 2 over ln 2. Correct? So, since a goes to infinity, negative 2 over a approaches 0. And then the answer here is simply going to be, for this integral value, is 2 over ln 2, which converges. So that means that the series also converges. Okay, so remember, the idea here is if you have the series that converges, I mean the integral converges and the series converges. Okay. This problem? So we're going to write that as an integral from 1 to infinity of 1 over square root of x plus 1 dx. So we're going to rewrite that with the limit. A approaches infinity. The integral from 1 to a 1 over square root of x plus 1 dx. Okay. You don't really need to use U substitution. You can, but it's a pretty simple one. So it's the limit as a approaches infinity. That's going to end up giving you 2 square root of x plus 1, going from 1 to a. Okay. And what we're getting here now is is going to be the limit as a approaches infinity of 2 square root of a plus 1 minus 2 square root of 2, right? And what happens is this is a constant value, but this is going to go to infinity, right? It's an increasing function, and that's going to diverge. So it's basically goes to infinity, diverges, and then from here we can conclude that the sigma from 1 to infinity of 1 over square root of n plus 1 diverges as well. Okay, so our last example here. So we have this expression 1 over a n plus b. So n is n obviously, but a and b just can be some positive values that we're going to be using. We just want to kind of generalize any expression in this form so you can quickly recognize them in the future. So we're going to rewrite that with the integral. So from 1 to infinity of 1 over ax plus b dx, which is going to equal, right, we're going to have to use the limit now. As well, I can't use a and b, so I'm just going to use c here. Okay, so it's the integral from 1 to c of 1 over ax plus b dx. I hope you can recognize it's a fairly simple one to do. The limit as c approaches infinity, this is going to give you ln 1 over a ln of absolute value of ax plus b. I actually do not really need the absolute value here because a and b are positive values, so it's going to be always positive, but we can keep that. It doesn't really matter that much. So we're going to have, oh, it's not a 1 over a, it's 1 over, oh yeah, it is 1 over a, correct. Okay, so we go ahead and rewrite that as the limit as c approaches infinity. So it's going to be 1 over a natural log of ac plus b minus 1 over a natural log of a plus b. Okay, so what do we have here? As c goes, well, this is going to be some kind of a constant. We don't know exactly what it is, but it's a constant. What we have over here is c goes to infinity, natural log goes to infinity, so this whole thing goes to infinity. This series is going to be diverging all the time, and that's for anything that's going to look like this. This is actually called a harmonic series. And one last thing that I want to mention here is I don't want you to assume when we do these problems that whatever, if you have a finite value for the integral, this is actually the value for the series. That is not really the case. As a general rule, the value of the integral and the value of the series are not going to be the same. Here's what I'm trying to say. Let me go to one problem. So when we did this problem here, and we got these answer of pi over 4, that does not mean that the series here has that value for the answer. There are other ways to evaluate those things, so just the only thing you can tell here is that yes, the series converges and this is where it stops. I hope this helps.